So welcome back. So we're going to do our next bit, which is we're going to do some more playing. We're going to do, well, if this thing has mass and it has velocity, it's got to have kinetic energy. And if it's attached to a spring, it's got to have spring potential energy. Basically, the energy is going to oscillate backwards and forwards between being spring potential and kinetic energy backwards and forwards, like mechanical systems tend to do. What we're watching when we look at the oscillations is exactly that taking place. We're just watching the manifestation of that mechanical energy, which is constant, going backwards and forwards between the two methods of storage. It's kind of, when you think about it from that level, it's kind of fascinating what's going on. It's like you go to the bank and you give it $100, and then they just decide to move it between your checking account and your savings account at some frequency that's nothing to do with you. It's all about the bank. It's the strangest thing. So, all right, we know that kinetic energy is equal to half mv squared. And we know V. We calculated V. So V is equal to minus A omega sine omega t. And so we say, well, my kinetic energy at any instant will equal 1/2 times m times, well, minus A omega sine omega t all squared. It's the V that's squared, so all of that is squared. And if I work it all out, I get 1/2 m omega squared A squared sine squared omega t. And okay, so that's one instantaneous term. And if I go to the other way and I say, well, let's think about it in terms of its spring potential. I know at any position my spring potential is 1/2 kx squared. And I know what x is. We worked that out, A cos omega t. So U, that should be a capital U, I'm sorry. That should be a capital U. So U is equal to 1/2 k, and then we have A cos omega t all squared. So then the next thing we need to do is need to get rid of this k. And we know that k is equal to m omega squared. Ooh, where did that come from? Omega equals the square root of m of k over m. Did I get that the right way around? If I have a bigger m, I have a lower, yes. So that means that omega squared is equal to k over m. And that means that, where's my equation? Yeah, k is equal to m omega squared. So that's where that comes from, yeah? So then we go, u is equal to 1/2 m omega squared, because there's my k, a squared cos squared omega t. If you look at these two guys, there's something kind of very interesting. They both contain 1/2. They both contain m. They both contain omega squared. They both contain amplitude squared. One's a sine squared, one's a cosine squared. So at any instant, because sine squared theta plus cosine squared theta equals 1, at any instant when one's small, the other one's big. When one's big, the other one's small. Yeah? So they're inverse of each other, if you like. And so what we get is that. Stop for a second. If I have an oscillation and I have that same oscillation with something with more mass, yeah, there's got to be more kinetic energy in there. Everything else has been kept the same. If I leave the mass alone, but the thing I mess with is the frequency, if I can get an oscillation and I have twice the frequency, it turns out it's containing 4 times the kinetic energy or 4 times the spring potential energy, which would not be obvious to me. And if I could keep everything else the same but change the amplitude, double the amplitude, I've stored 4 times as much energy inside there. So some things are obvious and some things not so obvious, but quite informative. If I remember that mechanical energy is equal to my kinetic energy plus my potential energy, then I can get the maximum of this by recognizing that sine squared theta can only equal at a maximum 1. So, all right, so that can be 1. So this will be K max. So my mechanical energy is the same as my maximum kinetic energy, which is 1/2 m omega squared A squared. And if I go the other side and say, well, okay, I'm always going to have this combination, and now for my maximum spring potential energy, my maximum spring potential energy occurs when that equals 1. So that would be a half m omega squared a squared. So we get the same value for the total mechanical energy as we should do. So when we're in the middle of the situation, I'm here. And when we're at the edge of the situation, I'm here. And if we're in between, I'm at one of these two. Okay? So it's really, I mean, if you think about it, we just developed something that is quite amazing, you know, based on Physics 1. If I basically think back about this, then if I want to get a quick way of working out how much mechanical energy could a system have, one of the ways is to say, well, what's its spring constant and what's its amplitude? I basically say, oh, it's going to be, if I remember that omega equals the square root of k over m, then I can kind of get to E mechanical energy is equal to half k a squared, which we kind of knew because when we have our maximum amount of spring potential energy, x is equal to my amplitude. Okay, so that should be pretty straightforward there. That's you kind of know. So very nice. It's a very nice system. So here, what I'm likely to do, I'm going to tell you, you don't have to learn these equations. You can figure them out, actually, but you'd have to learn them. But I'm not above giving you that equation and saying something like, oh, so if I were to double my amplitude, supposing that one spring system had a kinetic energy of 5 joules, and I kept everything else constant but doubled the amplitude to 10 joules, to twice as much, what would my new energy be? And I'd want you to be able to look at that and say, oh, it's squared, yeah? Where is it? I'd like you to be able to look at this and go, oh yeah, it's a squared, yeah? So I'd like you to be able to interrogate the equation. I might say, plot me a graph of k versus a. And you'd have to, oh, well, then it would be if that's k and that's a, it's going to be a parabolic graph. So there's skills. I don't want you to learn every equation in the book because I think you'll have a really tough time with it. So I'll try and be clear. You learn most equations in the book, but I'll try and be clear about the ones I definitely want to know and ones that I don't. Spring and block system oscillates with simple harmonic motion. 4 kilograms. Displaced 2 meters from equilibrium. Time t equals 0. System has angular frequency, omega equals 5 rads per second. What's the instantaneous kinetic energy? Okay, at t is equal to 1.3 seconds. So let's just start listing things. A is equal to 2 meters. Omega is equal to 5 radians per second. My t is going to be equal to 1.3 seconds. Let's have a look. My mass is equal to 4 kilograms. My omega, I've got my omega, I've got my amplitude, I've got my mass, I got my time, so I'm pretty well there. What was it? K is equal to, let me see, well, half m a squared omega squared, and now I'm dealing with kinetic energy, and kinetic energy was in terms of, was it sine? Yeah, sine omega t. So I go k is equal to 1/2, and I go 4, and I go 5 squared, and I go omega. Oh, so that was omega. What was a? 2 squared. 5 squared sine.
Professor, isn't that supposed to be sine squared? Yeah.
Sine squared, yeah, thank you. It's a good job I'm not telling you you've got to remember it. Sine squared and omega t. And omega t would be 5 times 1.3. So this would be k is equal to 2 times 4 is 2 4s are 8 times 25 is 200. 200 sine squared. 5 3s are 15, 6.5. I think I'm right in that. 5 1s are 5 and 5.3s are 1.5. 6.5. So k is equal to, get my handy dandy calculator. Now, to do this sine squared, there's no button on here for sine squared. I remember when I was a kid and I got my first calculator and I'd seen this in a book, kind of going, hey, it doesn't have all the buttons on it, but you know. What they really mean is sine omega t all squared, but it's the way they write it down. So I check them on radians. I go sine 6.5, close my brackets, enter. I go squared, enter. So I just did my sine squared times 200, enter. So I'm getting 9.255 or 9.26 positive, and that's joules. So not bad, yeah, not bad. Not bad. Notice my same layout. Do a diagram. If it's trivial, then you can just go to the equation, but most of the time I'll do a list. It jogs my memory. I write down my equation, I substitute numbers in, I do whatever steps I need, and then I get my answer. Put my answer in the box. Okay. Supposing we don't behave, supposing we don't move our block to the right hand side and let it go when t equals 0, supposing I let it go before t equals 0 or after t equals 0, or supposing I take it to the right hand side and I throw it a little bit, what do I do then? It sounds like I've got to start all over again, but it turns out I don't. If I just imagine a graph, so here's my position and here's my time. Yeah, this is really well behaved. I moved it to the right hand side and I let it go when t equals 0. So my t is starting from 0 and my position's where it's supposed to be. So that is x equals a cosine omega t. But supposing that I started a little bit early. So by the time t equals 0 came on my clock, I was already over the other side. How would I deal with that? And what I realize is it's the same shape of the trace. It's just my starting point's different. So I say, how much of a cycle is this difference? If it's half a cycle, if it's half a period, then I simply add on a phase angle of half of 2 pi is 1 pi radians. If it was a quarter of a cycle, quarter of an oscillation, I'd add on 2 pi over 4 radians. If it was a 16th of a cycle, I'd add on 2 pi over 16 radians. It becomes so simple just because of that. So this is called the phase constant or phase angle. It's represented by phi pretty universally. And it sounds like it's going to be awful. But it turns out it's going to be straightforward. If you look at the book, sometimes depending on whose book you've got, they'll have this in from the very beginning. That's the way I was taught. And I don't like that, because why make things complicated from the very beginning? And then the other thing you'll see is some books don't like to talk about omega. They like to talk about the frequency in hertz. And I am sympathetic with that. But the problem with that is it also makes the equations a bit complicated. I remember that omega is equal to 2 pi f. So if you want to talk in terms of frequency, every time you see an omega, you put a 2 pi f down. And that's pretty easily done. You know. And also, as a student, I never really got comfortable with omega until I really had to, because I could finagle the F, you know. So my answer is now just embrace the omega. It's kind of nice. A couple of bits. I know we've only got 2 minutes, so I'm going to just mention these things in passing. There's not much to know about them. If I take into account frictional forces, say caused by air resistance or fluid, then I will take energy out of my system. It won't be mechanical, it will become thermal, and it's lost to my system. And that must be manifest itself somehow. And if I look back here, the way that energy manifests itself for a given K and a given 1/2, if I change E, if I reduce E, I reduce my A. So my amplitude decreases. And that's what I see there, my amplitude decreases. So if you have friction, if you have drag, you're going to reduce your amplitude over time. And then the second thing is, so can we do math on it? And we can. You say, well, F equals ma, and part of the force is the restoring force, which is minus kx, and the other half of the force is a frictional force, which is minus a constant times v. Turns out drag forces depend upon velocity. And if I expand this, I get minus kb minus b times, not v, but dx by dt. I'm sorry, minus kx and minus b dx by dt. And that equals ma, which is m times d2x by dt squared. And that is a classic differential equation. And the answer is, I mean, that's what the book says, and the answer is this. And, you know, all I want you to realize is that your frequency, when you've got friction, is less than, that's a negative sign, less than the frequency when you don't have friction. Can you see that? So not only does the amplitude change, but the frequency changes. So that's all the two conceptual things I want you to know from there. And then the final thing I want you to do on this bit is I want you to recognize that if you have too little damping, you will overshoot the equilibrium. So you'll get a decreasing, but you'll get a little bit of a wobbly ride. And that's called underdamping. If you get it just right, you will go to the equilibrium position without overshooting as quickly as possible. And that is called critical damping. Not meaning being upset with, but it's vital damping. And if you overdamp, maybe you put syrup in rather than oil, so it's really viscous, then yeah, you will not overshoot, and yeah, you will go to the equilibrium position, but it will not be as quick as possible. And that is called overdamping. I'd like you to be able to draw these diagrams or name the diagrams if I give you the diagrams and ask for the name or whatever. Final thing. Know there's a thing called resonance when the driving frequency is the same as the natural frequency of the object. Know that that's called resonance. We're going to do resonance later, but know that it's called resonance, okay? And that's it. So, sorry to keep you